Hello students, today we are going to discuss the topic characteristic roots and vectors or eigenvalues and eigenvectors. These are corresponding to linear operators T from V to V, where V is a finite dimensional vector space over a field F. Let T from V to V be a linear transformation. If a non-zero vector V belonging to V satisfies TV is equal to lambda into V, then lambda is called eigenvalue of T, and every vector V is called eigenvector of corresponding to eigenvalue lambda. For example, that is, if TV is equal to lambda V, that is image of V under T, small v under T is lambda multiple of V, then lambda is called characteristic value or eigenvalue of T, and V is called corresponding eigenvector. For example, let T from R cube to R cube be defined as T x comma y comma z is equal to 2x comma 2y comma 2z. That is, TV is equal to 2v for all v belonging to R3. That means 2 is eigenvalue of T, and every vector V, non-zero vector V, which satisfy TV is equal to 2v. That is, all vectors in R3 are eigenvectors corresponding to eigenvalue 2. Note that if you have a linear transformation which is singular means at least non-zero, there exists at least V belonging to V non-zero, such that TV is equal to 0. For such a linear transformation, TV is equal to 0 for some non-zero V. This can be written as TV is equal to 0 into V, implies 0 is eigenvalue of linear transmission T, which is definitely singular, and every vector whose image is 0. Image is 0 means every vector V belonging to kernel T is eigenvector of corresponding to eigenvalue lambda is equal to 0. That is, every singular linear transformation has 0 as its eigenvalue, and every vector in kernel T is eigenvector corresponding to eigenvalue lambda is equal to 0. Second thing to note is if lambda is eigenvalue of linear transformation T from V to V, that means TV is equal to lambda V for some non-zero V belonging to V. That means V can be written as T inverse of lambda V. T inverse is also linear since T is an operator. We can say that V is T inverse of lambda V. That means V is equal to lambda into T inverse V. That means 1 by lambda into V is equal to T inverse into V. That means T inverse V is equal to lambda inverse V. That means lambda inverse is eigenvalue of T inverse corresponding to eigenvector V. Lambda inverse is eigenvalue of T inverse corresponding to eigenvector V, same eigenvector V. If V was an eigenvector corresponding to eigenvalue lambda, then lambda inverse is an eigenvalue of T inverse. Next theorem is something generalization of this theorem. If T is a linear operator and lambda is an eigenvalue of T with corresponding eigenvector V, then lambda k is eigenvalue of T raised to power k corresponding to same eigenvector V. That is, lambda square is eigenvalue of T square, lambda cube is eigenvalue of T cube, and so on. Proof will be by induction on N on K. For K is equal to 1, TV is equal to lambda V because lambda is an eigenvalue of T. That means lambda raised to power 1 is eigenvalue of T raised to power 1. Hence the result is true for K is equal to 1. Suppose results hold for K is equal to N. For K is equal to N plus 1, we want to prove lambda N plus 1 is eigenvalue of T raised to power N plus 1. Now t n plus 1 v can be written as t of t raised to power n into v, that is equal to t of t raised to power n into v is lambda n into v because of induction hypothesis. Result is true for k is equal to n implies t n v is equal to lambda n v, that is equal to lambda raised to power n into t of v, lambda raised to power n into lambda v is equal to lambda raised to power n plus 1 into v, that is t raised to power n plus 1 into v of v is equal to lambda n plus 1 into v. That means lambda raised to power n plus 1 is eigenvector of t raised to power n plus 1 corresponding to eigenvector v. Thank you so much.